Hello everyone, today we'll talk about the solution to the problem minimize XOR. This problem might be a little bit challenging if you're not familiar with bit manipulation problems, but if you have some familiarity, or at least you know how to think about problems like this, it's actually quite easy. Now let's get through the statement. First of all, our goal is to minimize some XOR. And how do we minimize an XOR? Well, first of all, how do we minimize a binary number? Well, we want it to have the fewest ones possible, and the ones that it has should be the least significant ones, the ones that are most to the right. In particular, if our number has a fixed number of bits, then we want those bits to be all on the right. So we have kind of an idea how to minimize a binary number. Now, how do we minimize an XOR? In particular, how do we minimize an XOR of a value that we control, this x, and a value that we don't control? And this is the crux of the problem. Well, we have a number, and that number has some bits set. And we want our number, the result, to have as few bits set as possible. Those that are set, we want to be the furthest to the right. So the first thing that we want to do is to unset all the bits that are set in num1. So if x has enough bits to cover the bits in num1, or fewer, of course we want to just start turning off the bits from num1, and we want to start turning them off from the most significant bits, because they contribute the most to the size of the result. And if we run out of bits while creating our value x, then this is the optimal solution. Just turn off the k most significant bits from num1. And of course, this k, this number of bits that we can create, is just the number of set bits in num2. So essentially we get num2, we get the bit count of num2, and this is the last time we ever care about num2. And what happens then if we turn off all the bits in num1 and we still have some bits remaining? Well, unfortunately now we have to start adding bits back and increasing the result. So we want to start from the least significant bits and just turn them off one by one until we cover all the num2.bitCount bits. Of course, we have to remember not to ever turn on again a bit that we turned off because it was turned on in num2 or in num1, because that's impossible, of course. We cannot both turn it off and on. When we XOR with a value that we control, we can flip a bit or not flip a bit, but we cannot flip the bit twice. So the final solution is to first of all turn off all the bits from num1, starting from the most significant ones. So this is the result we'll be building. We go through all the positions from 32 downwards. If there are no more bits for us to use, we don't do anything. Otherwise, if this bit is set in num, so we take num, we want to end it with a number that has a 1 on the position corresponding to that bit, on ith position, and zeros everywhere else. So this is just 1 shifted to the left by I. And if this end is true, that means that this num1 has this value set. In that case, we can unset it. One more bit is used. The result is ORed with, again, this value. So this power of 2, this 1 shifted to the left by I. And now we go from the other side, from the least significant side, and again. If there are no more bits to use, we don't do anything. Otherwise, we want to set that bit, so again, OR the result with 1 shifted to the left by I. Remember that this is one more bit used, but only if that bit was not set at the beginning. So if not, num1 and 1 shifted to the left by I. This could also here be just result, because of course the result after this, if after this whole thing we still have some bits that are unused, then after this loop the result is equal to num1. This is also maybe an optimization that you could use. And at the end we just return the result.